Welcome, curious minds, to another deep dive. Today, we're embarking on a fascinating exploration within the online encyclopedia of integer sequences, the OEIS. This is part of our series for number theory students, and today we're going to unpack OEIS A000341.
Ah, yes, A000341. It's got quite an elegant title, hasn't it?
It does. Number of ways to pair up 1.2, so sum of each pair is prime.
It feels like a really beautiful meeting point between, well, combinatorics and prime number theory.
Indeed it is. And this sequence, it's a fantastic example, really, of how conditions that seem simple, well, they can lead to some profoundly complex and interesting results. And it shows you how this sequence, which they classify as nice on the OEIS, actually progresses. It keeps you guessing a bit.
Okay, so let's maybe unpack that. We could look at the first few terms just to get a feel for it.
Good idea.
So for n and 1, the sequence value is 1. Just one way.
Right. Trivial, almost.
And then for n2, we get 2 ways.
Okay. Still small.
For n3, it's 3 ways, it seems. Linear.
It looks the way at first.
Yeah.
But then, bam. For n4, it jumps up to 6 ways.
Exactly. That's where it starts showing its more complex character.
So let's visualize that. n4 means we're pairing up the numbers 1, 2, 3, 4, 5, 6, 7, 8.
Correct. 8 numbers, so you need to form 4 pairs.
And the tricky part is the sum of each pair has to be a prime number.
That's the constraint. Every single pair. For instance, one of those 6 ways you mentioned. You could pair 3, 4, 4, 5, 8, and 6, 7. Let's check the sums.
Okay. 1 plus 2 is 3. Prime.
Yep. 3 plus 4 is 7.
Prime again.
5 plus 8 is 13.
Prime.
And 6 plus 7 is also 13.
Also prime. Okay, so that works. That's one way.
That's one of the 6. And, another valid one could be, say, 1, 4, 2, 5, 3, 8, 6, 7.
Let's see. 1 plus 4, 5 prime. 2 plus 5, 7 prime. 3 plus 8, 11 prime. 6 plus 7, 13 prime. Okay, that one works too.
Precisely. And the challenge, of course, is finding all such pairings systematically, making sure every number from 1 to 8 is used exactly once in each complete pairing solution.
That makes the jump to 6 feel more understandable now. It's not just picking pairs, it's making all of them fit the prime sum rule simultaneously.
Exactly.
So how do we go from counting these like this by hand almost to something more, I guess, mathematical? What's the actual formula or method here?
Well, there's a really elegant connection to linear algebra. The sequence value, an, can actually be calculated as the permanent of a particular n by n matrix.
The permanent, okay, remind me, that's like the determinant, but different.
Sort of. It's calculated similarly, summing products of matrix entries, but with the permanent, you add all the terms. There's no alternating plus and minus signs like in the determinant.
Oh, right.
And that makes permanence very useful for counting problems like matchings or pairings, which is exactly what we have here.
So what does this matrix look like for A000341?
Okay, so imagine an n by n matrix. Let's call it M. An entry, say, mij at row I, column j, is defined based on whether a sum involving I and j is prime. Specifically, the entry mij is 1 if the number I plus n plus j is prime, and it's 0 if that sum is composite.
I plus n plus j. How does that relate to the pairs like 22?
It's a way to structure the pairing possibilities. Think of I running from 1 to n, representing one set of numbers, and n plus j, where j also runs from 1 to n, representing the other set of numbers in the range 1.2. The permanent calculation then essentially counts the valid ways to pair them up according to the prime sum rule.
I see. So the matrix construction itself encodes the prime condition.
Exactly. And TD Ngo contributed a related formula back in 2007, often presented slightly differently using 2i plus 2j1 as the primality test within the matrix. But the core idea is this link to the permanent.
Wow. Okay. So the permanent poles in the linear algebra, the pairing is combinatorics, and the prime condition is pure number theory. It's quite a mix.
It really is. And what's fascinating looking at this sequence is how that simple-sounding rule sums to a prime dictates the results. The sequence goes 1, 2, 3, 6. Then the next term, a 5, is 10. Then a 6 is 24. Then a 7 actually drops to 14.
Drops. So it's not always increasing.
Not strictly. This irregularity really highlights the somewhat unpredictable nature of where prime numbers fall. It's not like a simple factorial growth. The specific distribution of primes really matters, especially for larger n. Finding these terms gets computationally quite demanding.
So wrapping this up for our listeners, for you learning about this, what's the big takeaway here?
I think it shows how OEIS A000341 is, much more than just a sequence of numbers. It's really a window into these beautiful, complex patterns that pop up when you combine simple ideas like pairing things up with the deep mystery of prime numbers.
And it all connects back to matrix permanence, which is maybe unexpected.
Quite unexpected for many, yes. It demonstrates those hidden connections across different mathematical fields.
So this deep dive into A000341, figuring out ways to pair integers so their sums are prime, it really underscores the depth you can find in number theory. It kind of invites you to think about how simple rules can generate these really complex, sometimes quite erratic patterns.
It certainly does. It pushes us to explore these hidden landscapes in mathematics.
And it leaves you wondering, perhaps, given how primes behave, is there even an upper limit? Or could these pairings theoretically keep growing, maybe bouncing around, forever? Something to ponder.